I don't have an opinion on that. But if you take 1 divided by that number, then every measurement in that unit gives you an integer.
Now I'm just thinking that when you've got this non-locality in space,
Yeah.
we have in quantum mechanics.
Yeah, that's here.
But Freudic actually suggested, well, what happens if you have the non-locality in time as well?
Yeah.
And you're sort of giving us some kind of tools to handle that.
That's what I perhaps dare to hope, that I should perhaps dare to think that, yeah.
Do you have a vision of where ultimately conservation orders, we see them down here, might find their expression in the non-commutative world?
Yes, well...
But we need that some order in
But
this.
Freddie hasn't got energy in there, you see, he's just got time.
This is mathematics. There is no vibrations or energy at the moment. But there is something I want to say, that you have here the commutative setup, but I didn't explain you this thing here, this sort of transversal section here.
Yeah.
And that's a commutative world again. So by blowing up the non-commutative geometry over a suitable interval so that you have enough points, you can make it a kind of strange cross intersection in this space. And that's the blow down, and that you keep it here. Again, at every moment this could be a different one, but for the physicist I think it would be good to assume that both space-time and this space are the same. Eventually, again, you can allow isomorphisms in the time, if you want. You don't have to. You can make your own example. But this is the dequantization. So I have a nice space. Whatever. This could be an algebra for me. This could be the polynomial ring, and I deform it into the Lie algebra, something like that. So I have a Poisson deformation. So I have a deformation quantization process. Then I have a dequantization by taking this transversal section in a certain interval of time that exists by my only axiom that there was a creation with enough points in the universe. Then I take the temporal points and I look at collections of, now these are sets of temporal points. And I get a commutative topology, a commutative space, and that is the observational mathematics. So here is how you think and you calculate with space-time. Here is the dynamical model with time as an index, and maybe a relation, I didn't put it, but as I said, you can make a map at every moment, a map from the big T to time in your space-time.
But what I was going to ask, what kind of restrictions would it be mapping from between the two times? What kind of restrictions?
Well, if there is a map, there should be compatibility of the movements.
Only that.
That's the only thing mathematically that I would assume. But I didn't even go that far because it's not necessary. It's a naked model, and I don't think it's necessary to assume a relation between the irreversible time and the relativistic time.
No.
But the physicist probably will tell me that they think there is a relation. Well, then make a map, and that's fine.
Yeah, but there are no really, except the internal, the whole.
Yeah, I only want the internal continuities to be respected. So the diagrams that come from the evolution maps, that has to be respected, and so that if you have a time here, which is an image of something, you go further, then you have a commutative diagram.
Okay.
That's all I would like to have then. Everything else is extra. But I didn't even put that for the moment. It's not necessary for what I'm saying. So there may be no relation between the irreversible time and the space-time because I'm not doing any physics anyway.
Right.
So that's up to you, right? But here is the interesting thing. Now, what is this? This is the mathematics of observations. Here is the mathematics of thinking. You think that you can describe it here until the moment that you observe. Because when you observe, you use time and you observe a dynamical process. Then you have this commutative description of the dynamical process because you want to calculate. And this was for a long time my pain, that I can do deformations in non-commutative geometry, but I cannot calculate. So by the sheafification argument, I philosophically am very satisfied because I will find a commutative space that approximates the non-commutative space at time t. And how does it approximate? Well, very well in my terminology, because the stalks, I have some sheaf theory here, for example, the stalks of the non-commutative world will be the same as the stalks on the commutative world. Same stalks. So if I have some temporal thing here, I have a stalk. Here in the projection, I have the same stalk. So
can you make it smooth somehow, or is it just an algebraic?
It's algebraic. Well, it's a sheaf theoretic. It's an isomorphism. Well, it depends. I'm so general that I take these sheaves in a certain category, and this can be an arbitrary category even.
So
and then the stalks in this category, and you look at the same category, of course, they are translated to the stalks in the commutative world here. Of course, you can imagine that this commutative world has to be much bigger than the space-time.
Yeah. But it still can be made to be smooth. Smooth in an ordinary
yes,
geometric.
so now we have to put on many more conditions. as I said, this is the naked theory, only using partially order and topological arguments. I threw away, after saying what I threw away all the rest for the moment. So it's naked. But
just when I ignore it, could you just say what in definition of the store? The definition of
I will come back. Yeah.
Okay, sorry. Just a few words, I mean.
Yeah, but somebody wants to crash course on sheaf here. Maybe I will talk a bit more about this.
Okay.
But so now you have, when you observe something, it is this kind of trajectory in time here, it is reflected, projected or blown down into this commutative world. And that's the mathematics of observation. This is where when you think theoretically, you're here. When you observe, you need this dynamical thing and you're here. So then when you look at the point, the smallest possible object to observe, what do you see? You only see it in the space-time when it is really a point, when it's idempotent. So from a certain moment you see a string. It's really like a string. And if you have these isomorphisms, if you allow these isomorphisms, the string can be closed. If you don't allow the isomorphisms, the string is always open. But since M-theory people say closed, that's why I think that it's nice that you move in time, you view this as an isomorphism of space-time, an evolution of space-time also. So then you can have closed strings and open strings. It was nicely drawn, but I think I have to go to PowerPoint. But okay, but how does the same point moving, how do you observe it? Okay, when you observe it, it is a temporal point. It's not a point at every moment. So sometimes it's a point, then you see it here. But it's not a point, not yet, the future point. Then it is only an open in that non-commutative topology. It's an open that will map to a point a little bit further. But then in this blow down, you will see it as an open in this commutative topology. There is a correspondence, it's an open. So what does it mean that this string here is a string of opens? So it's a tube or some higher dimensional string. And then this looks a lot like an membrane, right? It is a higher dimensional string. So, and that is specifically for the future of the temporal point. So things that look like normal strings here, they look like higher strings here when you observe. And I'm not sure. I'm in the paper I say maybe some string theory should look at this incident. Maybe it's sort of an incident. But of course, on the other hand, this is true. I proved it. It's mathematics. And maybe this means that if you want to do string theory, you can use this as a basis for the model. Because the string aspect is in the mathematics now. Right? And don't use any physics, they're not vibrating energies or whatever. They're just mathematical things about points in a non-commutative space. And they look like that. That's what I get. So you have real strings in the space-time, and you have these big brains, if you would, with these big strings in that observed world. This is commutative world. So then there's a lot of other things you can do. I didn't introduce a manifold, but a manifold